Welcome to lecture 19. In last lecture, we were discussing about the approach for the thrust augmentation. We were discussing about the need of afterburner, construction and operational details of the afterburner. Then we were discussing what are the requirements, why we are looking for the afterburner, and what all are the challenges with the afterburner. So, we must realize here the basic requirement for this afterburner, it is for the augmentation of the thrust, and that too it is very specific in terms we do not want to modify our whole engine. So, engine construction will remain same, we will be putting this additional component with the existing engine, and that is what will be acting with say augmentation of the thrust. That is what is a major requirement, and that is what is we are doing with incorporating this afterburner with two spool configuration. Now, let us try to realize, suppose if I consider this is what is my 2 spool turbojet engine. We were discussing about say augmentation of the thrust. The augmentation of the thrust, that is meaning we are looking for increase of our exhaust velocity, and that is what we have discussed. Suppose say we are looking for our exhaust velocity to be in this range. Under that condition, if I will be putting my turbine work, then it says my turbine entry temperature requirement will be very high, and we have realized we are having metallurgical constraint with the turbine blade material. At the same time, we are having mechanical constraints in terms of centrifugal forces. Now, under that condition, we have incorporated the afterburner, and this afterburner, as we have discussed, it is an additional component. That is what will be fitted with the conventional 2 spool turbojet engine. And here in this case, we can see this is our afterburner, where we are having fuel injector, we are having say flame holder, and then we are having say duct. In later part, on the rear part, if we compare the nozzles, these nozzles are different compared to our conventional engine nozzle. Here we are looking for variable area nozzle, because it need to handle large amount of mass flow rate, and this mass flow rate we know that is what is additional mass flow rate from our afterburner. So, we were discussing afterburner means we are having burner after main combustor or main burner, and that is the reason why we are saying that as a afterburner component. Now, when we are incorporating this afterburner, we can say the flow which is coming out from the turbine, that is what will not be going to say your exhaust nozzle, but we are adding the amount of heat at constant pressure here, and by doing so we are able to increase the temperature at the entry of the nozzle. And when we say we are increasing the temperature at the entry of the nozzle and the exit of our nozzle, we will see my delta H will be higher, and this delta H, that is what will lead to increase our exit velocity, and this is how we are doing the augmentation of the thrust. So, now you are clear with what all we were discussing. Here we have discussed about the specific fuel consumption and thermal efficiency consideration for say engine with the afterburner, and we realize my specific fuel consumption that will be very high when I am incorporating the afterburner, my thermal efficiency that will be lower, and that is the reason why we are not operating afterburner for continuous time. This will be for the short duration of time. Suppose if we consider we want to use for short takeoff, say special application, we understand it is for say navy, where my takeoff length will be very short. We want to do some maneuvers, there also we can use this kind of configurations. Now, let us look at what we mean. So, here this is what is representing our J52 Pratt and Whitney engine. Now, let us try to understand with the afterburner. So, this is a cut section of J79 GE15 turbojet engine. So, here in this case, if we look at careful, then here we are having this afterburner which is been incorporated, and this afterburner that will be followed by say afterburner pipe, and this pipe that will be connected with the nozzle, and this nozzle, as we have discussed, is a variable area nozzle. Since my temperature at the exit of my afterburner or say before entering inside the nozzle it is very high, that is what is required special kind of cooling. And if you recall, we have discussed about say afterburner liner incorporation, where we are having different kind of cooling mechanism, that is what is being used. Now, if we consider there are many engines, say especially for the 2-spool turbojet engine with the afterburner, they are JE79 as we have discussed, which is say incorporated with the Lockheed F104. We are having Pratt & Whitney J57, it is for Bomber B52, Rolls-Royce and Snecma Olympus, that is what is very famous engine. It is been incorporated with the Concorde. It is commercial aircraft which was flying at the supersonic speed, that is a special requirement. Then we are having say Rolls-Royce A1 200 300, that is what is being used for say powering sub 35 Draken. We are having Tumansky R25, that is what has been used for MiG-21. So, you can say almost all engines with afterburner, they are being used for the military purpose. The exceptional case is with the Rolls-Royce Snecma Olympus engine, which is being used for the Concorde aircraft. Now, let us try to understand the cycle, because that is what is of our major concern, and this course it is dedicated for that part only. So, let us try to realize this part. Suppose if I consider this is representing my TS diagram. On this TS diagram, this is my atmospheric condition. We are having very first component, it is intake, and for this intake we are having say process from infinity to 2 to 3, that is what is representing my LP compressor, 3 to 4, that is what is representing my HP compressor, it is a compression process. This I am representing at this moment is an ideal cycle. We know we are having the heat addition which is happening at the constant pressure, and that is what will be used to raise the temperature at the entry of the turbine, and we can say this is what has been raised from 4 to 5. So, 5 is nothing but it is our turbine entry temperature. Now, very first component what we have is our HP turbine. So, 5 to 6, that is what is representing the expansion which is happening in HP turbine. 6 to 7, that is what is representing my expansion in LP turbine, and after LP turbine we are adding our heat at constant pressure. Suppose if I consider I am not having afterburner, then my process will be ending from 7 to 9. Now, since I have incorporated the afterburner, so we are adding the amount of heat at constant pressure, and we will be raising our temperature to 8A. Now, that is what will be subjected to say nozzle and process 8A to 9A, which is representing our say expansion process which is happening in the nozzle, exhaust nozzle. So, you can realize almost we are able to increase the velocity, exhaust velocity maybe 2 times or 3 times. It depends what will be our say afterburner temperature. Okay. Now, suppose if I consider we are interested in actual cycle, because that is what is our requirement. So, let us try to realize that part in terms of actual cycle. So, here if we consider this is representing my TS diagram. Similarly, we are having our atmospheric air from where it is entering inside my intake. So, this is representing my intake. Since my intake, as we know, we will be having the losses, that is what will lead to increase say the entropy, and that is the reason my point, that is what will be different from the ideal process. From there my flow will be entering inside the compressor. This compressor is say LP compressor, and here this is representing my actual process. From here this will be subjected to our next compressor stage, we say it is HP compressor, and actual process that is represented by this red line. So, just understand, if we compare our ideal cycle and actual cycle, my temperature at the exit of my compressor stage, that is what will be higher than that of my ideal cycle. Now, we are looking for raising the temperature. So, we will be adding the heat in the combustion chamber. So, here in this case ideally we are assuming the heat addition process to be constant pressure process, but in actual we will be having the losses, and those losses that is what will lead to reduce the pressure within the combustion chamber. It is represented by P05. Now, here this is what is my turbine entry temperature. Now, the expansion process ideally it should be 5 to 6, but in actual we will be having the expansion process that is represented by this red line. Now, here if we look at, it says my exit temperature from the turbine, that is what will be higher than that of my ideal process. Now, from there my flow which will be entering inside my LP turbine, there we will be having the actual process, it is represented by this line. Now, what next component we have, suppose if I consider I am not having say afterburner, or I am having afterburner, but I am not operating, under that condition my process will be represented ideally by 7 to 9. Okay. Now, from there my flow it will be enter inside the afterburner. So, afterburner we can understand it is a device where we will be having lot of losses in terms of friction, pressure loss, total pressure loss which will be happening, and that is the reason why my pressure will not remains constant within the afterburner. So, my exit pressure from the afterburner will be not P07, but it will be P08. So, this is what is representing my actual process which is happening inside the afterburner. Now, from here my flow it will be entering inside the nozzle, where the expansion process that is what will be happening. This ideal expansion process we can say it is represented by 8AA to 9A, but in actual condition we will be having the expansion, that process is represented by 8AA to 9AA. Under this condition we can say we are having the maximum temperature of the cycle, that is what is say T08AA, and basically we will be having the loss of pressure, that is what we are representing here as delta P in the afterburner. So, now you are able to understand what we mean by ideal cycle and actual cycle. You can easily plot this. So, just try with plotting of this ideal cycle and actual cycle without committing any mistake. Now, let us try to analyze this part what we say. So, let me consider the component as afterburner component. So, my entry condition for the afterburner here, if you look at this, entry condition is 7 and exit condition is 8. So, let me put it here, this is what is my 7 and my state 8, and here I am adding my say heat by means of say burning of the fuel. So, the entry heat we can represent in terms of m infinity into 1 plus f at 0.7. Same way at the exit we can say there is a change here in terms of m infinity into 1 plus f FAB 808A. Here we are having addition about the fuel, that is what we have represented in terms of fuel air ratio of the afterburner. So, now we are interested in how much amount of fuel need to be added in order to raise the temperature to say T08. Okay. So, under this condition we can write down our mass balance, we can write down our energy balance. This energy balance it is m dot 7 at 0.7 plus this is my amount of heat what we are supplying, that is what is equal to m dot 8 808A. Now, if I will be simplifying this, this will be given in terms of m infinity into 1 plus f at 0.7 plus this is what is my m infinity into FAB QR. Here this will be m infinity into 1 plus f plus FB into H 08A. Both the side I can remove, I can cancel out my m infinity, and that is what will lead to give me my fuel air ratio, that is what is required in the afterburner. So, you can say this equation, this formulation, that is what is representing my amount of fuel, that is what is required inside the combustion chamber. or inside the afterburner. Now, if we are considering the actual cycle, let me give you some time to you. Maybe you can draw your control volume. Just try to put the formulation in terms of input heat, output heat, and what is amount of heat what we are adding in our afterburner. So, can you please try with? Let us look at. Okay. Now, here in this case, what will be the change? So, if I draw my say control volume here, under that condition we are having additional component which is coming into the picture. It is my afterburner efficiency. Since this is what is a combustion chamber, a type of combustion chamber, so that also will be having efficiency slightly on the higher side. Okay. So, we can write down our mass balance. Same way we can write down our energy balance. As I have told, we are having say afterburner efficiency, that is what will be coming into the picture, and the formulation, that is what will be changed with say afterburner efficiency. So, be careful whenever you are solving your numerical or whenever you are doing your design calculation, do not forget to incorporate this afterburner efficiency. Okay. Now, since this is what is known to us, the next component what we have is our nozzle. So, let us try to look at how to move with the nozzle part. So, this is what we say here in ideal cycle. I am having my expansion from 8A to 9A. In the case of actual cycle, this is separately been defined in terms of 8AA to 9AA. So, if we consider, we are interested in say calculation for what will be my exit static pressure, what will be my exit static temperature, what will be my exit static density, because we are interested in calculation of exit velocity, we are interested in calculation of exit area. So, similar to what all we have done in terms of say earlier cycles, here my critical pressure ratio, that is what will be calculated in terms of P08A divided by PC, that is what is been represented in this formulation. Same way when we are incorporating the actual cycle, that is where it is separately been written in terms of P08AA, and here I will be having nozzle efficiency. So, do not get confused. On top specifically it is been mentioned, it is say ideal cycle and actual cycle. So, now the situation is we will be calculating our critical pressure. So, let us see when we are doing our critical pressure calculation, if my critical pressure is coming greater than that of my atmospheric pressure, we can say my nozzle it is working under choke condition. When I say it is working under choke condition, we can say my exit pressure, that is what will be equal to my critical pressure. Okay. Now, this is what is common for almost all engines, what all we will be discussing. So, you need to be very careful in terms of what is the meaning of nozzle to be in a choke condition or nozzle is unchoke condition. So, based on that we can calculate what will be our temperature ratio. Say both the cases we will be calculating our temperature ratio. This temperature ratio, that is what will be giving me what will be my exit static temperature. Here for ideal cycle it is T9A, here this will be T9AA. We can calculate our velocity here. Now, this velocity similarly if I consider I am having configuration, it is say unchoke condition. When we say my critical pressure, that is what is lower than that of my atmospheric pressure, under that condition we say we will be having our exit pressure, that is what is my atmospheric pressure. Okay. Now, for this also we can calculate what will be our temperature ratio, and for that temperature ratio we can calculate what will be our exit velocity. Okay. Now, here this thrust what we are representing, it is basically m dot infinity into 1 plus f V9. So, just realize the case here my mass flow rate, that is what has increased, minus V infinity plus P9 minus P infinity into A9. So, what it says, if we are having say afterburner, that is what is being incorporated, then I will be having my delta H, that is what will be higher, and it says my T08A, that is what is very high compared to my turbine entry temperature. Then it says my exit velocity, if I will be having my afterburner which is operational, that is what will be approximately equal to 1.5 times the V9 when my afterburner is non-operational. So, just understand what is the meaning, why we are looking for the operation of the afterburner. But same way you need to realize what all are the limitations also. Now, with this, let us try to understand the actual cycle analysis when we are having say afterburner which is being incorporated, because this is what is important in terms of doing our cycle analysis. No doubt many things what we have discussed earlier, this is equally applicable here, but for the sake of brevity let us discuss this part. Here very first component what we have is our intake or the inlet. For that we know what is our diffuser efficiency. This diffuser efficiency, it is correlating my isentropic work divided by my say actual work. Here in this case we will be having our exit pressure which is been correlated in terms of diffuser efficiency. In line to that we can calculate what will be our exit temperature. Now, we are assuming our process which is happening inside the intake as a adiabatic process, and that is the reason my temperature, that is what will remains same. So, I say my enthalpy H02 equal to H01, or we can say my T02 equal to T01. This is what will be helpful to us in terms of calculating our exit pressure and temperature from the intake, and this will be the input parameter for our next component, that is my LP compressor. So, let us look at the LP compressor. This LP compressor, that is what has been represented in terms of ideal process and actual process. So, we know our compressor efficiency. This compressor efficiency, as we have discussed, is a function of my pressure ratio and polytropic efficiency. Since we are using say axial flow compressor, where we will be having more number of stages, and because of number of stages we are considering polytropic efficiency rather than considering say adiabatic efficiency or isentropic efficiency. Now, this is our pressure ratio, we say P03 by P02. Once we know this pressure ratio, we can calculate what will be our temperature ratio. Based on this temperature ratio, we are able to calculate our exit pressure and temperature. Now, once we have information about exit from my LP compressor, that is what will be the input parameter for my HP compressor. So, let us discuss about the HP compressor. So, for HP compressor also we can write down the efficiency correlation as we have written for our LP compressor. Okay. We can calculate or we can have our compression ratio, that is what is P04 by P03. We can calculate what will be our temperature ratio, and based on that we will try to calculate the pressure and temperature at the exit of our HPC. Now, this is in a sequence. Now, this will be the input parameter for my combustion chamber. So, for combustion chamber we can draw our line diagram, we can put our control volume approach, and if we will be putting our heat parameters, then based on our understanding we can calculate what will be our fuel air ratio. So, here in this case be careful, since we are discussing about the actual cycle, that is the reason we will be having burner efficiency, that is what will be coming into the picture. Same way for the actual cycle we will be having loss of pressure, and as we have discussed 2 to 5% loss, that is what will be happening inside the combustion chamber. So, here we can calculate what will be our fuel air ratio. Again, let me put the point here, many times this fuel air ratio, that is what is known to us from the required specific fuel consumption, Under that condition, we are interested in calculating what will be our turbine entry temperature. So, you can do this calculation both the way. So, be careful about this part. Okay. Now, what we have next is our HP turbine. So, for HP turbine, we are having our ideal process which is been represented by 5 to 6, but in actual case, as we have discussed, we will be having our temperature to be higher. So, under that condition, here in this case, we know our HP turbine, that is what is been used to rotate my HP compressor. So, we will be doing our work balance. So, let us put the work balance HP compressor work, that is what is equal to say my HP turbine work, and here we are incorporating the parameter which is called mechanical efficiency, and as we have discussed, this number will be in the range of 75% to 85%. Okay. So, if we will be writing our equation in terms of work, we will be able to calculate what will be my exit temperature from the turbine. So, we have our efficiency term for the turbine. From this efficiency term, we can calculate what will be the exit pressure from the turbine. This turbine is my HP turbine. So, we can say we are able to calculate the important parameter at the exit of my HP turbine, that is T06 and P06. Okay. Now, what next component we have is my LP turbine. So, let me give you chance to write down the formulation for that. So, just try to put the equation, let us see how you are moving with. Okay. So, here also I will be comparing my work, my LP compressor work and my LP turbine work, that is what will be same with the incorporation of my mechanical efficiency, and here in this case if I will be doing my work balance, then we are able to calculate what will be my exit temperature from the LP turbine. Okay. Same way, in order to calculate my exit pressure, I will be taking the help from say my efficiency term. So, it says my LP turbine efficiency, that is what is correlating in terms of pressure and temperature. So, based on that, we are able to calculate what will be the temperature and pressure at the exit of our LP turbine. So, I am moving a little fast at this moment, because these things are known to you and this is what will be coming again and again. Okay. So, just do practice for this part, that is what will be building the confidence for you. Now, what we have our next component, that is what is my afterburner. So, for afterburner, as we have discussed earlier, you can write down the equation for the energy balance. So, here in this case we are putting our mass balance, we can put our energy balance. As we have discussed, in afterburner we will be having drop of pressure, that I am representing as say delta P in afterburner. My temperature, that is what will be maximum temperature of the cycle, and here if we will be simplifying this, it says this is giving me the ratio of fuel and air. So, it is for afterburner. So, just look at this formulation carefully. Okay. Now, here as compared to my previous relation, we are incorporating the efficiency term, that is what is my afterburner efficiency. Okay. Now, let us look at the next component what we have, that is what is my nozzle, and for nozzle, as we have discussed, we will be doing our calculation for say critical pressure ratio. Since this is what is my actual cycle analysis, I will be having my nozzle efficiency, that is what will be coming into the picture, and if we are putting that, and if we will be having our critical pressure that is greater than that of my atmospheric pressure. So, we will be considering exit pressure as a critical pressure. Okay. So, be careful, do not forget to introduce this parameter called nozzle efficiency. If you will be not considering this, it may possible that your actual case nozzle is choke, but your calculation will come as nozzle as unchoke, and you know the consequences of that. If this is what is wrong, your exhaust velocity will be wrong, your thrust will be wrong, at the same time your thrust specific fuel consumption also will be wrong. So, be careful about the calculation for the nozzle. Now, here in this case we can calculate what will be my temperature, and based on that temperature we are able to calculate what will be our exhaust velocity. Okay. Now, similarly, if we are having our nozzle, it is under unchoke condition where my critical pressure it is lower than that of my atmospheric pressure. Under that condition we are considering our exit pressure as atmospheric pressure, and for that we can calculate our exit temperature, and the equation for this exhaust velocity, that is what will be given in this formula. Okay. Now, once we are able to calculate our all velocity component, very next requirement for us, that is what will be in terms of calculation of performance parameters. So, if you try to look at here, since we have incorporated our afterburner, that is the reason my thrust equation, that is what will be changed, because here this is what we are writing in terms of my exhaust velocity. So, this will be my exhaust mass flow rate. So, it is m dot exhaust into V 9 minus m infinity into V infinity. That is the reason it is say 1 plus F FAB. Be careful about this part. Same way here in this case, this is what is representing my pressure thrust. For that we can write down this equation. Now, if you are comparing your result with afterburner operation, without afterburner operation, so your formulation, that is what will be majorly changed for the thrust. Same way when we are talking about the thrust specific fuel consumption, this is not m dot F divided by thrust. Here in this case it will be m dot F plus m dot F of afterburner. Specific thrust formulation, that is what will remain same. Now, in terms of my propulsive efficiency, as we have discussed, this is what is in terms of say my exit mass flow rate, and that is the reason why this is what has been represented in terms of 1 plus FAB. Same way when we are calculating our thermal efficiency, my formulation, that is what will be changing. Here this is change, it is not m dot F into QR, but this is what is basically m dot into 1 plus F into QR. Okay. And we can calculate our overall efficiency, that is what has been given in terms of propulsive efficiency and thermal efficiency. So, I am sure this is what will be giving you the confidence in terms of doing say cycle analysis for say 2-spool turbojet engine with afterburner. Same logic, same process, that is what is been applicable for the single spool configuration also. Now, what all changes that will be happening in performance parameter calculation, that is what has been given in terms of my thrust specific fuel consumption, propulsive efficiency, thermal efficiency and overall efficiency. Now, with this we are ending this lecture. In next lecture we will try to use these fundamentals for the calculation. We will be taking one tutorial problem where we will be discussing how to do the analysis part. Thank you very much.